Hello all. So now we have learned about rectifiers and how rectification is done. Now we know that when you give an AC signal to a rectifier, we get DC voltage, but we know that this DC voltage contains much AC component, right? But our intention was to get absolute perfect DC signal. But that part is not completely fulfilled when you do the rectification. You get AC is converted to DC, but still the AC component is quite significant in the output signal, right? So in this context, now we are going to learn what are filters, because they do a particularly specific job of getting our intention of producing more exact DC signal from the AC signal. Okay, so we'll discuss about this in detail in this particular lecture. Now first we are going to discuss about the function of a filter. Now what is a filter? Here on the left hand side is shown as the rectified DC output voltage from a full wave rectifier. Since we have both cycles, we can say this is an output of a full wave rectifier. Okay, now suppose you have the filter circuit here, and to the filter circuit you give the full wave rectified DC voltage. Okay, then after, now we don't know what is happening within a filter, but then basically it is a circuit which produces some output. But how the output will look like, we can see that this output will be almost very smooth. In the case, in the input signal, if you see, input signal was having it was really a sinusoidal kind of a voltage variation, but that much variation is actually is not there in the output voltage after filtering, right? So now we see that here after after the filtering part, you can see that the signal has lost much of its AC component, or much of its variation in the rectified DC voltage is now lessened in the output of the filter. Thus we can say that the output of the filter still have a little bit of varying component. It still have an AC component in that, because it's still varying, but then it is far better than the rectified DC output voltage. So after filtering, what we see is that the much part of the AC component is lost, and the output is almost a steady DC voltage. Okay, so we'll say finally what we'll say that thus we can say that filter is a circuit which removes, or you can say minimizes, because it is still some kind of a fluctuations are there. So I can say this circuit is a filter is a circuit which removes or minimizes the unwanted AC component of the rectifier output and allows only the DC component to reach the load. So finally you will be measuring the output across the load. So across the load you will get much of the DC component rather than the AC component. So we can say that filter is a circuit which removes the unwanted AC component of the rectifier output, okay, and allows only the DC component to reach the load. Okay, so this is the input rectified DC voltage to the filter, and this is the filtered output voltage from the filter. Okay, now we'll discuss furthermore, that is how a filter can basically be designed. Okay, you know that the passive circuit elements like inductors, capacitors, resistors, they are used in several circuits. Now when they have peculiar features that when they are used separately or when they are used in combination, they show some peculiar type of properties which help us to do the filtering action. That is, when you give an AC signal, means rectified AC signal, DC signal to these components, either they are alone or they can be in a combined form. So because of the basic electrical properties of these circuit elements, this output from these elements, or output from these passive circuit elements, can be uh, can be more a filtered output. Okay, that is, AC component can be filtered out, or you can get more DC component in the output voltage. So this is basically done or made fabricated using these inductors, capacitors and resistors, or their combination. Okay, now there are basically mainly four types of filters, and we'll be discussing here. This one is inductor filter, second one is capacitor filter, third one is inductor capacitor filter, or we call it as LC filter, and the fourth one is pi filter. So from the name itself you can make out what are the basic components used in the filters. Okay, so in the first session we'll study what is an inductor filter. Okay, so from the name itself you can understand that this filter is made out of inductance coil. Okay, so we can see what is happening here. So here inductor is suitably placed between the rectifier output and the load resistance. So here we use an inductor between the rectifier output and load resistance as shown in the figure. You have the rectifier output here, okay, and then an inductance is connected. Okay, inductor, you know, it is a coil, and within that magnetic core is placed. Now this is the inductance coil, and now you have, in series with that, you are connecting a load. So we can say that the inductor is placed between the rectifier output and the load resistance, and output is measured across this load resistance. Now we have to think what basically happens when current flows through this inductor. Okay, so now we'll think about it. Think, and if the current which you are getting or passing through the resistance, or the inductor, is basically an AC rectified DC voltage, but then it has AC component as well as DC component, right? Now inductance, you know the impedance of an inductance? Yeah, you know, you have learned in your small classes that it has this inductance coil has its impedance, and it has a reactance part which offers resistance to the input AC voltage, or it offers resistance to the AC component. And this impedance, or this reactance which offers resistance to the AC component, you have learned that it is normally denoted by the symbol XL. XL. And you know what this XL is? Yeah, this XL is omega L. Okay, that is, I will write it as omega L. And what is this omega? You know what is this omega? This is 2 pi f. You have learned that this 2 pi into f frequency, and this is the value of the inductance coil L. Okay, now this, what is this frequency we are talking about? It is the frequency of the AC signal, because DC doesn't have any, DC is not fluctuating one, right? So DC component is a steady voltage, so it doesn't have any fluctuations, which means DC frequency is 0. But AC currents frequency is something which what we say as the frequency. But we know that in an AC supply the frequency of the AC signal is 50 hertz, right? Now this F is, so the basically depending upon this frequency will be the XL value. Okay, suppose when you go on increasing the frequency, what happens? The reactance will also increase. right? So now you consider the DC signal. DC doesn't have any frequency, that means F is 0. So for DC, this we know that the reactance part is 0. But then we have to think about AC when we the input of the or the output of the rectifier has a significant component of AC, and that AC signal have a frequency, right? So which means that for the AC, this F value is quite significant and your XL value will be quite high. So what it means is that for an AC signal, the reactance will be significant. So for an AC signal, if the reactance is significant, which means that AC signal to the AC signal, this inductor offers quite significant resistance. So that means that AC signal is very difficult to flow through the inductance coil, but the DC signal will easily pass through because the reactance part is 0. So it doesn't offer much resistance to the DC component. So DC component will be easily passed through this coil, while the AC component will be blocked by the inductor. So what is appearing across the load will be what? Yeah, what appearing across the load will be the DC component. So you understood how the AC is actually filtered out, or you will get finally the DC component only across the load. Okay, but still you know that lower frequency components of AC will be a little bit transferred through the inductance coil, but higher components will be exactly blocked, but lower frequency components will pass through the inductance coil. So you will have a little amount of AC component in the DC, but still it will be the AC component will be very, very low, because inductance coil offers significant reactance to the AC signal or AC component. Thus I can say that when current passes through an inductor, it offers high resistance to AC component and low resistance to the DC, right? Thus AC component is blocked and DC component only reaches the load, and that is how an inductor filter produces more DC or more amount of DC component from the rectified output from a rectifier. Now we will see what is the input signal. This is the input signal here without filter, that is the supply from the rectifier. So the rectified output is like this. It is a sinusoidal kind of an oscillation, okay? But then, and you know, this is the maximum peak voltage of the peak voltage, or we call it as Vmax or something. Here it is marked as VLmax. Okay, now this is the average DC. You know that average DC VDC, and that is 2 Vm by pi, and it is marked here. So this is the average level of DC. Now what you get across the load resistance is basically not the perfect DC, but still a small variation in the DC, but still it will be having an AC component overriding along with the DC voltage. So you will have a small fluctuation still, but then it is quite the fluctuation is very, very small compared to the original supply from the rectifier. So this is how the output voltage from the across the load will look like. Okay, so this now this is about the inductor filter. Now we can see basically little more about it. That is about, first we are going to see the ripple factor of an inductor filter. The ripple factor of an inductor filter is numerically gamma. It can be calculated as gamma equal to RL divided by 3 root 2 into omega L. This is divided by 3 root 2 omega L is in the denominator. Now you see what is RL. RL is the, we have seen in the previous slide that RL is the load resistance value. Okay, so this is RL, and then omega is the angular frequency, and then that is which is equal to 2 pi f. And what is L? L is the inductance value of the coil, inductance coil, and it is normally represented in terms of Henry. Okay, so this is how ripple factor can be found out. Now what you understand, you know that a perfect filter is something which has very little ripples, right? That is, AC component will be very much lower when the ripple factor is low. Now, for the ripple factor to be low, what is the condition you can identify? Yeah, load resistance should be very low. So one thing is, for a ripple factor to be, ideally ripple factor should be low. So when to ripple factor should to be low, what we can say is this RL should be low, okay, and also the inductance coil is high. In the value of the inductance coil should be high. So this lower RL values and higher L values basically guarantees a good ripple factor value for an inductor filter. Okay, but then so in that way I can say that the ripple factor it is more effective when the load current is heavy. But what it means, that is, only when the load resistance is low. When the load resistance is low, we can say that the load current is high. Okay, so I can say, what I can say is that the inductor filter is more effective in the sense the ripple factor will be low when the load resistance is low, or I can say when the load current is high. So first thing is it effectiveness. I'm discussing about effectiveness. So the inductor filter is more effective for heavy load currents or small load resistance. Okay, then the second thing is we already said that again, for the ripple factor to be low or for an inductor filter to be more effective, the inductance value should be very high. Okay, so one thing is inductance value high. So we can say that it is effectiveness for its effectiveness. It is effective when the high for heavy load current. Second one is it is effective when large inductor values are used. But then you have to think one more thing. When the inductance value increases, one more part is there, that you know that the inductance coil, apart from the reactance, that is its resistance to the AC component, it also has the actual resistive part, that is the resistance it offers to the DC component, and that is this normal R. So the inductance coil, apart from this XL value, X value, that is the reactance value, it has its inherent R value also, R property also, that is the resistance which the inductance coil offers to the DC component. So it has this R value also. This inductance coil will have an R value, or it will have a basic resistance to the DC component as well. Okay, but then as you increase the inductor value, what happens is that the DC resistance value will also increase. But then if you increase the DC or if the DC resistance value of the inductance coil increase, what happens is that the output DC voltage which you get across the load will go decreasing. That is, the output voltage across the load output DC voltage across the load will be lowered. That is, you usually contain a VDC which is equal to 2 Vm by pi, and that DC output voltage will lower. Okay, so finally what we can say is that for an inductor filter to work more effectively, it is better to use small load resistance, or we can have high load currents. The second one is we can have larger inductor values, but we have to be careful, because larger inductor value may increase the DC resistance of the inductance coil, so that may lower the DC output voltage. So we have to optimally design the inductor value so that the ripple factor will be lowered, and as well as your DC output voltage will be somewhat significant, or what you expect. Okay, so these are all about the inductor filter. So today in the session we understood what basically a filter circuit is, and what are the 4 different types of filter circuits, and we discussed more in detail about the inductor filter, where you keep an inductance coil between the rectified output and the load resistance, and then you understood how the inductor filter basically work to carry out the filtering action. Okay, then we discussed about the ripple factor of an inductor coil. Then we understood what all can we do, or what are the different cases in which the inductor filter are more effective. Okay, so thank you, and if you have any queries, please post it. Thank you very much.